Warning, the video you're about to watch contains mathematics at the level of differential calculus, also known as Calc 1. All material has an assumed prerequisite of pre-calculus and a full semester course in trigonometry. A thorough review of prerequisite topics can be found by searching the web.
It's the system of equations. We must deal with them all at once. Always looking for solutions. Positive outlook overcomes.
At noon, Ship A is 150 kilometers west of Ship B. Ship A is sailing east at 35 kilometers per hour, and Ship B is sailing north at 75 kilometers per hour. How fast is the distance between the ships changing at 4 p.m.? So I've read the problem. I'm going to call that a win. Step one, I've read it. I will say, yep, I sure did. Good for me. Step two is understand. And to understand this problem, I had better draw a picture. There's just no other way I could do this. I have a ship that's directly, west of another ship initially. Ship A is going to be sailing due east, and Ship B is sailing due north. So I am going to plot things out like this. I'll say here is Ship B initially, and here's Ship A again initially. So I'll say A naught, B naught. I'm going to denote the way they're traveling using arrows. So again, at noon, maybe I should call this A12, right? Well, no, because then A4 would not. Well, yeah, I'll do it in military time. A12, B12, there we go. So A is at that position at noon. B is at that other position at noon. Let's see, A is 150 kilometers west initially. So I'm going to write that in. This distance right here is 150 kilometers. That's the initial distance between them. Ship A is sailing east, and east is to the right here, so it's going this direction. And its velocity, or its speed, or well, it's going to be its velocity, is 35 kilometers per hour. So I will just say 35 kilometers per hour. We're going to worry about the mathematics of it a little bit later. Meanwhile, Ship B is heading due north at 25, again, kilometers per hour. There we go. And the question is, how fast is the distance between the ships changing at 4 p.m.? So this distance might shrink to here, let's just pretend, and that distance might shrink to there. And we're curious, at exactly 4 p.m., how quickly is that distance D changing? So again, at 4 p.m., so here's, where's my black pen? Here's B at 1600 hours, and here's A at 1600 hours. That's 4 p.m. And we want to know how quickly is that red line changing? Is it shrinking? Is it growing? And if so, how quickly is it shrinking or growing? So far, I think visually, I kind of know what's going on, right? We always have that red string connecting the two boats together, and it's shrinking or growing. We just want to know how quickly that is happening. So I kind of understand what's going on now. The next thing I need to do is label. And this is labeling things that have been given and labeling things that I want, things that I don't know. I find it's often easier right after doing this first step of kind of drawing a picture. I find it's often much easier to label what I want than what I have. So what I want to know how quickly D is changing. So I want the derivative of D with respect to time when time is equal to 1600. Or basically when it's 4 p.m. Maybe I should just write that. When at 4 p.m. So I'll say at 4 p.m. I want to know how quickly that distance is changing at 4 p.m. That's the only thing I want. I don't want anything else. But they gave us some information here. So let's see what we were given. And there are a lot of things that we were actually given, but there's only a few things that will really help us out here. When we're given things, I'm really hoping they gave us rates. And if you think about it, they really did give us some rates. For example, the easiest rate is this one. The rate for Ship B. That blue distance right there, and let me use my blue pen. This blue distance right here, they told us how quickly that's increasing. That distance is increasing at a rate of 25 kilometers for every hour. So if I call this distance B, I know that the rate of change of B with respect to time is 25. They gave me that. That side length is growing 25 kilometers for every hour. On the other hand, this side, maybe I should have drawn this in green instead. So this green side right here, that entire green side is shrinking. That is what I'm going to call side A. And I happen to know side A is shrinking at a very specific rate, right? It's not increasing. That green line is actually decreasing. So when they get to here, that green line, this, let's just say this is A right here, rather than that. That green line is shrinking. So it's getting smaller and smaller and smaller. And actually, I like the idea. Let me do some erasing because I really want to showcase something here. I like the idea of calling this leg right here A, because then it really showcases that I'm using a right triangle. That will help me build a master equation relating A, B, and D. So I tell you what, let's call this side length, oops, wrong color. Let's call this side length A, which we actually already did. We'll do the blue side length B, which we already did, and the red side length D. Now we happen to know the rate of change of A. Ask yourself, is side A increasing or decreasing? You should know it's decreasing. If you're wondering, well, what if it got on this side? Well, just ask yourself, how far has that boat gone after 4 hours? 4 hours later at 35 kilometers per hour, that's what, 140 kilometers? That's not 150, so it's still somewhere over here. So the distance is still shrinking. So I happen to know the rate of change of side A with respect to time is a negative, because it's shrinking, 35. It's shrinking at a rate of 35 kilometers every hour. Initially, at the very beginning, when boat A was way over here, boat B was actually right here, but let's just look at it this way. Initially, the boat's moving along. The distance is still shrinking at 35 kilometers per hour. It was just got a long distance to go, but the rate never changes for the boat. Anyhow, so those are the givens, and we listed out what we want. There really is one more piece of information we were given, which is that the initial distance was 150, and that'll come into play when we build our master equation. But you could write that at the given column. So you could say that A at time 0 or time 12 is equal to 150. You could say that if you want. That's totally fine. They did give us that. So I've labeled as much as I can. And now I need to create a master equation. And the master equation has to relate, that's why it's called related rates, these variables that are in these derivatives, A, B, and D. If you take anything away from this lecture, it's that. Whenever you have derivatives, you want to relate the variables within those derivatives, A, B, and D. And if you can find an equation here based off our picture, good for you, right? It's the Pythagorean theorem. So our master equation is going to be A squared plus B squared is equal to D squared. That's it. Now we're going to go ahead and take derivatives. So I'll go ahead and check that off. Now it's time to rate equation. Rate equation. Nice thing about implicit differentiation is that you don't need to call A like 150 minus 25, whatever. You don't have to do that. You can just leave it as A. You can leave B as B and D as D. Totally fine. Just take the derivative with respect to time. The derivative of A is going to be twice the derivative a squared, is going to be twice a to the first times the derivative of a with respect to time, plus the derivative of b squared is twice that b times the derivative of b with respect to time, equals the derivative of d squared, which is twice that d times the derivative of that d with respect to time. Notice I didn't call that distance, that red distance, I didn't use a lowercase d because I knew that I was going to take its derivative, and d dt looks really weird if they're all lowercase d's. You can divide everything by 2. I'm not going to erase because it's kind of unfair if I do that, so I'm just going to go ahead and do this. It just makes it nice when you can clean this up a little bit, right? There we go, equals d dt. So I'm done with that. 6, which is a sub and solve. Sub and solve. I just made up something there. All right, so I'm going to go ahead and sub in dB dt is 25, dA dt is negative 35. I know that initially the distance was 150. That's what A was, but we're not worried about that. We're worried about what is the distance at 4 p.m. So I'm going to sub in. This is our sub in step. We're going to let dB dt equal 25. I think that's what it was. Yeah. And dA dt equal negative 35 and time equal 4 p.m. All right, let's do this. That will imply, well, we'll leave A alone, but we'll call this negative 35 for dA dt. We'll leave B alone, and we'll sub in 25 for dB dt, and we'll leave D alone, dd dt. But now we have to actually do a little bit of thinking. Not too much though, but just a little bit. We have this right triangle. It kind of looks like this, honestly. Side length B. So that boat has been moving at 25 kilometers per hour for 4 hours. Remember, this started at noon. So side length B at 4 p.m. is 100. Again, 25 kilometers per hour for 4 hours. Side length A, on the other hand, that started out at 150. This is where that 150 comes in. And you lost, what was it, 35? 35 kilometers per hour for 4 hours. That's 121.40. And so side A is of length 10. From this, you can find side length D using the Pythagorean theorem. It's the square root of 10,100. I think that's right. Right? B squared plus A squared there. So that's 100 plus 10,000. So 10,100. So I'm going to sub in those. That's my 4 p.m. snapshot. Sub those in. I get 10 times negative 35 plus 100 times 25 is equal to the square root of 10,100 dd dt at time 4 p.m. Dividing both sides by that square root, and you'll get to a number that you'll need a calculator for, because guess what? That's just how related rates work. It doesn't work out beautifully because these are real world problems. And so this ends up being, what is that? 2,500 minus 350 is 2150 maybe? And yeah, and that's over the square root of 10,100. And I just grab a calculator and I get approximately 21.4, and that's kilometers per hour. So sub and solve and then state the solution, I guess is what I would say here. So my solution, I'm just going to state it out loud, is that the distance between the ships is changing at 21.4 kilometers per hour at 4 p.m. So this distance here is changing. So dddt is approximately 21.4 kilometers per hour. So it's moving that quickly, the distance between them at 4 p.m. Notice that my substitution step doesn't happen until I've built my rate equation. So there is a reason why we wait until after we take our derivatives to substitute. If you were to substitute before you took your derivatives, let's say that I substitute in constants before I take my derivative. So I substitute in constants right here. The derivative of a constant is 0. And so you essentially zero everything out. So do not substitute until after you take the derivative. Once you take the derivative, you could substitute all day long. I don't care. But don't substitute anything prior to taking the derivative. That's just important to note.
It's the system of equations. We must deal with them all at once. Always looking for solutions. Positive outlook overcomes obstacles getting in our way. Cause affects more than we can sometimes see. Things for what they are and work together until you feel at peace. Just listen close. Don't talk too much that isn't kosher. You may really hurt inside. It doesn't justify you to speak too loud and cry.